Our last speaker for today is Maxim Kontsevich, and we were just hearing a bit about Calabi-Yau manifolds in a different setting, and so now we'll hear about Calabi-Yau motives.
I apologize, I'm really not very good in preparing presentations, so to essentially you should suffer my bad handwriting here. So I will speak about not Calabi-Yau varieties, but Calabi-Yau motifs, and it's something closely related. And what it's all about. First, I'll just remind you what is really nice about motifs. So motifs, it was a kind of concept introduced by Grothendieck. This you don't have any strict definition. So you start with two fields, little k and capital K. Little k, it will be really the most important field. You consider algebraic varieties, algebraic geometry over this field. Would be finite field, rational numbers, complex numbers, and so on. And it will be filtered by any characteristic. And this capital K, it's kind of auxiliary field. It's coefficients. You consider motif is these coefficients in this capital K field, which eventually will be something very simple. And characteristic 0, we'll see next page. So what was the original approach which Grothendieck proposed? And in fact, Yuri Manin, when he visited IHS in '68, he talked to Grothendieck and wrote first paper about motifs. It's not Grothendieck, but Manin wrote this paper. So you start to think about natural direct summands of cohomology of algebraic varieties, say smooth projective algebraic varieties, defined over this little k field. And there was too many homology series, and one for varieties of a field which is part of complex numbers in field of characteristic 0. We just consider associated complex algebraic variety and consider its usual homology. It's called Bethe homology. But also for field of characteristic 0, you can calculate the rank homology in algebraic way. It's Grothendieck, once of Grothendieck's contribution. Also, you can calculate italic homology. You consider covered by finite pieces and take finite coverings of things and get homology with L-adic coefficients. So there are many cohomology series, but they give spaces of the same dimension. And in fact, one can compare one thing to another. So you see that's kind of different aspects of the same hidden structure. And what Grothendieck wanted to kind of define this structure intrinsically without any specific homology theory. So what you do, you consider smooth projective varieties over a field small k, and now you want to make a kind of some direct summand of each cohomology. How to make a direct summand? You should produce an operator on cohomology. And cohomology could be in many different senses. And operators one can do make in the following way. Consider some finite collection of subvarieties, maybe singular, in the square of your manifold of middle dimension, and consider linear combination of these cycles. In homology theory, any subvariety should give a fundamental class, and using Poincare duality and intersection, one can interpret, understand the thing as correspondence, kind of multivalued map from your variety to itself. You can multiply, and you want this guy to be projector. This capital K appears as a coefficient for this subvarieties which have nothing to do with your small k field. Usually it's rational numbers. So you get a projector, and you project to the image, and you get some piece. And different pieces of different varieties could be the same motif. So that's a rough idea of what is a motif. It's a direct summand given by such projection. There are many, many attempts. People try to define things which will satisfy all expected axiomatics, and up to now there's really no good success. There are various approaches by Mori, by Vygotsky, by Ayub. So we don't have a really good definition, so it's hard to write a paper about the subject because it is, you should specify what you mean by motive. It's, different people have different meaning theories. And it's, in fact, possible that this original idea of Grothendieck use projectors, it's not sufficient. Yeah, so it's maybe motives belong to some kind of larger constants. Not, of course, it's really designed to be part of algebraic geometry and cycles, K-theory, and so on, but maybe it's something more. For example, it was kind of implicitly understood in the definition that you have enough algebraic cycles. If you have a projector, and which is given by something with respect to all cohomology series and comparison isomorphisms, it should be given by cycles. But it's not clear that it's true. Instead, it's kind of similar to, it's closely related to what's called Hodge or Tate conjecture. Hodge conjecture says that if you have algebraic variety over complex numbers and you have cohomology class with rational coefficient, such that it's represented by PP form for certain number field, then it should be represented by a cycle. But already from Andre Weyer proposed a really huge family of possible counterexamples. Some abelian varieties with high even dimension with a very small complex multiplication by imaginary quadratic field have exotic kind of things, Hodge cycles in the middle degree, and nobody knows how to construct them algebraically. So maybe just think it's really wrong. And so, in fact, Deligne, about 25 years ago, developed a kind of theory of absolute Hodge cycles, imagining that these Hodge-Tate conjectures are wrong, but there are some kind of things which behave as algebraic cycles, but not represented by any algebraic things. Yeah, and if it's true, that it means all ideas by people starting with like Voevodsky motifs and so on are very off the target. Yeah, so it's not relevant to what really goes on. Yeah, so it's one possibility. And also, just about 10 years ago, I suggested a kind of general viewpoint that if you try to see what we have with motifs, the commutative algebraic geometry, it's completely, it's just a special case of some more general non-commutative algebraic geometry. And it looks that motifs belong to a larger kind of framework, all things formulated much more nicer, at least. But once again, it's a very speculative thing. But so it's maybe it's part of non-commutative algebraic geometry just from the beginning. And what we kind of know about motifs. Now, I put in parentheses, it means that what is the expected picture. Yeah, first of all, about the coefficient field, this capital K, I didn't, there's really not much interesting to say. This ultimate kind of coefficient field, which you can use in any situation, which is part of algebraic numbers called complex multiplication closure of rational numbers. It's some infinite extension of rational numbers, but strictly smaller than all algebraic numbers. And it's maximal Galois extension of rational numbers in which complex conjugation, which will be element of the group, is a central element. So it's essentially, you consider equations where all roots are real and take quadratic extensions. Yeah, so that this part of the story is not interesting. But now for the real question about this small k field. If it's a finite field, there is a clean conjecture. It was maybe formulated by by Milne. For example, consider prime finite field with prime number of elements. The simple motifs with coefficients in this complex multiplication thing are the same as Weyl numbers, which appear in conjecture, or when you count points on variety of finite fields. It's the same as irreducible polynomials with almost integer coefficient. You get denominator 1 over p, and all roots should lie on a circle with a radius which is half integer power of prime. Yeah, that's for finite field. And now for rational numbers, so for number fields, there are two really great conjectures which are not much talking to each other. One was explained by Richard Taylor. It's Langlands program. It says that simple motifs or number field, and simple with this coefficients are essentially the same as some Caspedal automorphic forms with integer, but some of very special kind. There are much more automorphic forms which simple motifs. Automorphic forms have some parameters associated to various primes, in particular at Archimedean places. They have some complex numbers, and these complex numbers should be integer. Morally, you can think that if you consider Hodge structure of some algebraic variety, it has Hodge decomposition, and these indices for Hodge decomposition are integer. And in Langlands parameters are analogs to the things which could be complex numbers, not integer numbers. And 99% of all automorphic forms, or maybe even more, 99.999 is your talk, yeah, are in a sense, if you count naturally, are not related to arithmetic at all. Yeah. So in automorphic form world, we have a much larger source of things, and the rest, which do not come from motifs, is not related to anything at all in mathematics. Yeah. It's actually kind of very strange. You have there's a kind of math forms, the eigenfunctions of Laplace operator on model curve, and for them there's really no kind of algebraic geometry, anything. Yeah. So some people speculate that actually motifs are part of a larger word which are automorphic forms, but we don't know what does it mean. Yeah. Nobody has any idea why this conjecture works. Yeah, so and also there's, of course, this great progress by Richard work. You see that automorphic forms are solutions of some PDE, and it's very hard to solve PDE, and unless in some special place when you have considered harmonic representative of closed differential forms. This is some kind of topological part which exactly correspond to what Richard solved, that motifs when all Hodge numbers are equal to 0 or 1s. All this HPQ are no more than one-dimensional. Yeah. So the Langlands conjecture, kind of one of final goals to explain what kind of mystery of L functions in number theory. When you take product of prime numbers as counting things, and the things should have meromorphic continuation. Yeah, it's explained. That was explained through automorphic picture. And another great conjecture. It's also completely unmotivated. It's a Belinson extension of early conjectures by Deling. Belinson conjectures about completely different question. If you have what I told you about kind of pure motifs, consider smooth projective varieties, and Hodge structure are pure. But then one consider mixed Hodge structures and also homology of open varieties or singular varieties, and get mixed things which not related directly to Langlands picture. And then because you have some kind of non-semi-simple situation, you get X1s between pure motifs. And Belinson conjectures is about dimension ranks of these X1 groups. And also he proposed a formula for values of L functions at integers. So both Langlands conjecture and Belinson conjectures say something about L functions, but in a very different world. And this is very something bizarre in Belinson conjecture. The dimension of X1 group is related to action of this complex conjugation on Betti realization. Yeah, it's just interpolation for some results here and there without any explanation. Yeah, so it's kind of experimental mathematics. Yeah. So there are two things which nobody have any idea why they're true and how they're related to each other as well. Yeah, that's a kind of these things. But now one can ask, even without understanding, what one should expect from motifs over larger fields. So what are larger fields? You just consider fields of kind of like rational functions and several variables. And essentially, it means that you should ask what are modular spaces of motifs. Like, and motifs, you can, like an original picture, you can see like variety and some correspondences. You should deform variety and correspondences. So you should get something like finite dimensional schemes of rational numbers, like modular space of abelian varieties. Yeah, in fact, people didn't thought much about this, how to formulate the equation, and it's really very puzzling, because first of all, if you get a motif, some pointer, you give some point in a modular space, and in practical terms, you think about variety and find collection of cycles and weights. What will be the tangent space? Because it's variety of your some field, the tangent space and you deform get a modular space, it should be vector space, presumably finite dimensional of the same field. Okay. But X1, at least in Beilinson conjectures, are essentially vector space over rational numbers, which is not really of this field K. It's, they have a different meaning. And dimension of X1 group from Beilinson conjecture seems to have nothing to do with the formation of our motifs. And it's strange, because if you have any kind of additive equation, you have some representation of some algebra, and you get some kind of additive category, then deformations of objects of this category, like motifs, should be governed by first X1 from this object to itself. And it seems to be not the case at all. And also, I was really puzzled by this object motifs, because if one can try to think about various equations in mathematics, one can have modular spaces, and whenever you get modular spaces, one can divide some kind of derived viewpoint. Also, it's related to what Jacob was telling us. So it's, in all reasonable equations in mathematics, which you can kind of algebraic nature, when you get modular space, you get some kind of derived deformation theory, because X1 is part of maybe high X groups. Yeah, so, and for motifs, what the tangent space, it's not clear what at all, and what should be higher tangent space, it's, again, absolutely not clear. Yeah, so it's really a very unhealthy situation. Yeah, so what is derived deformation theory of motifs? How to formulate it? And so now I go to the goal of my talk, to make some proposal, which I have already for several years, but it's very hard to formulate precisely, so it will be kind of really dreamy part of my talk. So the idea is that the kind of the central things should be analog of Calabi varieties in world of motifs. And this will be, and all theory should be kind of centered about this class of things. And the modular space should be really smooth manifolds of kind of controlled dimension. So you get plenty of nice smooth manifolds as a parameter spaces. And these spaces are similar. In fact, we'll be generalizing what people use in a lot in kind of Langlands picture, Shimura varieties. This was a particularly simple class of motifs. You consider Hermitian symmetric domain and divide by arithmetic group. And in fact, these Shimura varieties, typical examples are modular space of abelian varieties. I'll explain they parameterize in infinitely many ways Calabi motifs. Not Calabi varieties, but Calabi motifs. And what is nice also, this Calabi, at least heuristically, these Calabi motifs, if you consider the modular space, they have natural derived extensions. We get derived modular space, which in this case will be actually some nice, again, algebraic varieties. So first I have to start with Calabi property in geometric sense, not in abstract motivic sense. So Calabi variety, it's smooth projective variety, or let's say field with a field of complex numbers with trivial first channel class, or it means that it has algebraic volume element, non-vanishing everywhere. they're interesting by many, many reasons, particularly in birational geometry or from mirror symmetry. And they also have kind of remarkable differential geometric property. It's a theorem by Yao, proof of Calabi conjecture, that such manifolds carry calorimetric with zero Ricci curvature. Yeah, like these G2 manifolds also have zero Ricci curvature in 7-dimensional real case. Yeah, so it's a very exceptional object, and I think the kind of the greatest property of this variety is its theorem by Bogomolov, Tian, and Todorov, that the moduli space of complex structures is smooth. It could be not a manifold by orbifold because variety can have finite group of symmetries. And dimension of the space is kind of controlled. You consider Hn minus 1, 1. What does it mean? Consider n is the dimension of my Calabria variety, complex dimension, and I consider cohomology classes represented by forms which are n minus 1 holomorphic and n minus 1 times holomorphic and 1 times anti-holomorphic forms. Yeah. Notice if consider, because it's only one holomorphic forms, it's Hn0 has rank 1. So it's next Hodge number to number 1 in Hodge decomposition of the middle cohomology. Yeah, so here, in fact, one can deform algebraic variety to non-algebraic one, and one can modify the things to speaking about the algebraic deformations to replace cohomology by primitive part, and it will be deformation of excess algebraic variety as well, if you don't stay in algebraic geometry context. And this theorem has many proofs, and one of kind of later proofs was based on deformation, kind of abstract deformation theory with some differential graded Lie algebras and so on. It gives you a natural derived extension of the moduli space. And this derived extension is also smooth. And the dimension of the moduli space, it's kind of dimension of all middle cohomology minus 1. This 1 corresponds to pretty trivial part. It's better to remove it. And in fact, this derived moduli space is an honest usual algebraic variety. It's not derived something. It's algebraic variety with action of C star, algebraic action of C star, which has a fixed point, which is usual moduli space, and the rest is contracted to the fixed point. Now, so it's some nice object of, in a sense, conventional algebraic geometry. The tangent space at fixed point has C star action, so it's graded. It's just direct sum of H1 of my manifold with coefficient of tangent sheaf, which is described usual deformation, and H2 with wedge square of tangent sheaf, and so on. And because it has a volume element, one can identify exterior powers of polyvector fields with forms, and see that you get direct sum of Hodge components, graded Hodge components, and just you fix the ambiguity of the choice of volume element, you say that it's direct sum multiplied by dual space to one-dimensional space Hn0, corresponding to holomorphic volume form. And from the first description, consider cohomology description polyvector fields, you see it's commutative associative algebra. You can just get exterior product. It's non-unital because I remove unit. Yeah, so we get just commutative associative algebra, like positive cohomology of some, let's say, Grassmannian. So we get this thing. Yeah, so we see that this natural structure there. Now, go to motivic world. What are Calabi-Yau motifs? So one can make the following definition. Maybe it's not final definition, but Calabi-Yau motifs, it's a simple motifs when considered motifs with ultimate coefficient field Q bar with complex multiplication, and such that the lowest term in Hodge filtration, which is in the RAM realization of any motifs, we can see the RAM cohomology, has dimension 1. So if you consider sequence of Hodge numbers, you get 0, 0, they get First non-zero number will be 1. And then I get some next number d. And one kind of try to formulate, I can do it precisely, kind of lousy conjecture, that the modular space of such guys is smooth of the dimension which will be next number. And if consider associated gradient to the RAM realization, just let's go back to this previous thing. This direct sum of think it's associated gradient with respect to Hodge filtration and multiply this dual space to this one-dimensional guy. It has natural structure of commutative associative algebra over my field small k when my motive is defined. Yeah, so that's kind of interpolation from geometric results. Yeah, first of all, about Bogomolov-Tian-Todorov theorem, together with Lyudmila Kotsarkov and Tony Pantev, we kind of couple of times collaborated. We tried to generalize this proof with differential gradient algebra to other circumstances. We get many other examples when the proof works. But here the structures A and B are kind of straightforward. We get automatically, it's kind of really imitation of the original proof. The nice thing is that we get not really cohomology of variety, but some direct summands and sometimes with coefficients in cyclotomic field. So it's not just usual cohomology. But then one can try to make some experiments because at least in mirror symmetry, when consider mirror duals to some rigid Calabi threefold, you should get something bizarre. For example, consider some rigid three-dimensional Calabi with very high symmetry. The mirror object is the following. You consider cubic hypersurface in 8-dimensional projective space. It's not the Calabi variety, it's Fano variety. So Ricci curvature is positive. But then, if consider middle cohomology, it will be 7-dimensional variety. In the middle, it looks like you get numbers, a lot of zeros, but then you get 1, 84, 84, 1, 0. So it looks like third cohomology of 3-dimensional variety. There's no such 3-dimensional variety. But then you count how many coefficients you have for cubic equation, subtract the dimension of the group JL9, you get exactly 84. Yeah. So and here one can produce really many classes of examples. Here, for example, here what are numerics here? We get Calabi given by equation, like say in degree d in d variables, and get projective space dimension d minus 1. Here we get equation degree 3 in 9 variables, and 3 divides 9. Yeah, so we can make such equation degree 10 in 100 variables, or you can make some complete intersections. And for many, and you study for which complete intersection the first non-trivial Hodge number is 1, and miraculously always you just make long calculation with third class and numerics. Next number is always equal to the dimension of modular space. I don't know why, because this proof with differential gradient algebra doesn't work at all. Yeah, so it's really good for me. It's very strong evidence to this conjecture about Calabria motifs that it goes beyond manifolds, beyond Calabria varieties. And in fact, these Calabria motifs one can really produce them by thousands. You take any pure motif, just take some cohomology or some pure projective variety or direct summands, and it has a Hodge filtration. There's some notation. Yeah, for example, think about the RAM cohomology of some projective variety, and Hodge filtration take in a Hodge decomposition, take direct sum of first terms. The beauty of Hodge filtration is that it's defined purely algebraically in terms of algebraic RAM cohomology. Yeah, so you get this Hodge filtration. Then you take some exterior power of this guy. And what is exterior power? You take n's exterior power, and n will be the dimension of this term of the filtration. And if you think in a second, you see immediately that in this exterior power, this lowest term of Hodge filtration will be top exterior power of this term of Hodge filtration for original guy, so it will be one-dimensional. Yeah, so you can produce these things just taking exterior powers of anything. And yeah, there's a really funny thing here about this exterior power with a degree of exterior power is the dimension of a term on Hodge filtration. It's exactly the same thing appears in Beilinson conjecture when he wants to predict values of L function. He takes exactly this exterior power. And it looks what he predicts as the value of L function, it's a volume of real points of some Calabria variety, in a sense. Yeah, so this Calabria are secretly present in L function world. And in fact, what in Beilinson conjecture, he considered even mixed exterior power of some mixed motifs. So presumably want to do the same thing with mixed motifs as well. Yeah, there is also one kind of delicate point here. When you take exterior power, this guy could be not necessarily simple. It's not like Galois representation will be not decomposable. When you take a simple summand which contains this lowest one-dimensional piece. Yeah, so you can, but for a new guy, you can repeat the construction. Can you it will be much larger dimensional motif. You take again Hodge filtration and again get exterior power. So yeah, so there's really tons of Calabria motifs, much more than Calabria varieties. And one can play this kind of the simplest example. You take first cohomology of some curve, let's say of genus at least 3. So the Hodge numbers, if you consider cohomology, just that 2 non-zero Hodge numbers is G and G with G is a genus. Now consider middle exterior power with G. The group which acts on this H1 is symplectic groups, and so this will be not in decomposable representation. Take primitive part, and then for primitive part, it will be Calabria motifs. Motif in what are Hodge numbers? So the smallest one is 1. The first one is 1 because Calabria motif. Next one is G times G plus 1 over 2, which is dimension of moduli space of abelian varieties, which is bigger than moduli space of dimension of moduli space of curves. Yeah. So this conjecture A thinks that it's you can deform your motif in a very large family. Kind of predicts that you can deform this exterior power of first cohomology of a curve by something which is more than just deformation of a curve. Now, of course, it's kind of a very clear example. One can understand anything. But now, from this cohomology of curve, one can construct this cohomology of abelian variety. But one can again take exterior power or any representation of corresponding what's called Hodge state group. And it's really very easy just by hand-waving argument to show that if you consider any representation of this Hodge state group for first cohomology of a curve, such that lowest Hodge number is 1, then the next number will be exactly dimension of this corresponding Shimura variety. And moreover, you get this huge space. This automatically will be commutative associative algebra in intrinsic way. It's some simple representation theory. Yeah, so we see that the Shimura varieties, which are more or less moduli space of abelian varieties, are moduli space of infinitely many very different Calabria motifs of various rank. Yeah, and all things work. So the what this conjecture was saying, I just repeat myself, that if you have a curve, we have very small moduli space of curves, but then we had abelian varieties, which are Jacobians of curves. And this Jacobians has much larger family, which will be kind of optimal family for this Calabria motifs. But now we can try to ask equation for the surface. If we get a surface and we take of general type, maybe with large, many holomorphic forms, capital N will number holomorphic forms, we take exterior power of the second cohomology of surface. It's algebraic surface. Then should be Calabria motif. Then should be deformed, but we have absolutely no clue what to do. Yeah, so this conjecture make a prediction that you can do, invent some analog of Jacobian, which depends which kind of varies better than the surf itself. And in fact, one can, Claire Wazan noticed that one can easily produce kind of counterexample. It's a bit technical. For example, consider four-dimensional hypersurface, maybe in, I forgot, in P5, I think. Yeah, I forgot exact dimension. So you consider, consider some surface, something of general type. And, but you consider four-dimensional objects, but then for a large subvariety in moduli space, they develop some algebraic cycles in the middle. You can remove these algebraic cycles. And these algebraic cycles do not affect anything in this boundary Hodge number, so it will change exterior power, so you get some kind of a little bit of contradiction. So it looks that in this equation, one should maybe add auxiliary summands which without affecting two bottom Hodge numbers. Because in the deformation theory, in this property, I said the lowest Hodge number is 1, next is the dimension, but the rest, it's maybe not necessarily simple motive. Yeah. Yeah, so it's a little bit of dirt here in this picture. And another challenge, you get a product on the things which describe completely intrinsically in terms of the RAM realization. We consider associated gradient with classical Hodge filtration and cancel one-dimensional, lost one-dimensional space. This should be a commutative associative algebra. And how to see it from any kind of arithmetic data, it's absolutely not clear. So it's a big challenge how to produce it. And again, I have no idea, but it looks to be a good question. Essentially, extract if you choose a basis in the RAM, essentially, if you choose some basis in the RAM homology, you should extract rational number. But for this, again, I have no idea, and that's a good question. Thank you. Yeah, for example, yeah.
Some part the subquotient where their functor would act.
Of course, in example, you see this interesting story because we consider motifs also with coefficients, not rational numbers, but there are some correspondences with complex multiplication fields. So it's this part, I think, lacks categorical interpretation. When coefficients are rational, it looks in examples really some kind of full subcategory of coherent sheaves and so on, but otherwise I don't know. Sorry?
So the Hodge structures are parameterized by the exceptional tube domain?
Domains have Schmur varieties, yeah.
Does that have, does what you're describing allow you to say anything about that coming from something more?
No. People speculated about Calabria varieties with Hodge numbers 127, 27, 1, but this is a very special case when the modular space is locally homogeneous, yeah, but no, this other modular spaces are not homogeneous at all, yeah.
So this won't tell you anything about the meaning of those?
No.
Oh.